In this video, we're going to be working out a ballistic pendulum problem that is going to take a series of steps. We're going to take a look at the launcher itself, firing a 50-gram ball, and then find out the initial launch velocity. And then we're going to apply that velocity to this situation over here, and then use some momentum and energy ideas to compare the theoretical final gravitational potential energy to the final experimental gravitational potential energy, and then see what that percent difference is. So the first thing we're going to do is implement some acceleration and projectile motion ideas. Now, as everything stands here, we're going to convert this to 0.05 kilograms to start off with, to make sure it's in the right units to put into our formulas a little bit later on. We don't need that in the beginning, but we'll definitely need that a little bit later on, taking that 50 and then dividing it by 1,000. Now we're going to have to do two different things. We're going to have to find the time it takes to reach the ground, which is going to take one formula, and then we're also going to find the horizontal velocity needed to make it land at 1.4 meters. So at this point, you've already measured the height that the ball is off the ground. So we'll say that's exactly 1 meter, and then also some kind of delta x value of where it landed. So we got that 1.4. So at this point, we have a delta y value of -1 meter because it's displaced 1 in the downward direction, and then we have a delta x value of 1.4. So let's go ahead and solve for the time first, and then go ahead and use that time to solve for our horizontal velocity, and utilizing this 1.4 as well. All right, so I plugged in my values into the delta y equals VIT. Our initial velocity in the vertical direction is 0. So we're allowed to make this beginning part 0 plus 1/2 gt squared, g being -9.8. So I combined these two to have a coefficient of -4.9 in front of the t squared. So all I had to really do is 2 steps, divide both sides by -4.9, and then square root each side, and then I got a time of 0.45 seconds. Now, the 0.45 seconds can be applied in any direction because it's not a vector, and that would be the time that it's in the air, because the horizontal velocity has no effect of the time in the air. So with that being said, v equals delta x over t in the x direction. So we have our delta x 1.4 by finding our landing position experimentally, and then divided by the 0.45 seconds. 0.45 seconds right there. And then we have a velocity of 3.11 meters per second in the end. So that's going to be a good start to our second part of the problem. We know the initial velocity of our projectile is 3.11 meters per second. Now, what we're going to do is do some momentum concepts and calculations to figure out the initial velocity of the ball and the pendulum together. So again, we're going to do a little conversion and then change that mass to 0.1 kilograms by dividing by 1,000 and scooting the decimal 1, 2, 3 places over to the left. So we're going to write out all the momentum of everything before the collision and after the collision, and let's find out the velocity of the ball and pendulum combined afterwards. we know all the momentum of the system before and after the collision is going to be equal. So our ball has a velocity of 3.11, which we found earlier, plus the 0 of the actual pendulum itself. And then afterwards, because it's an inelastic, perfectly inelastic collision, we have both of the masses combined with one single velocity because now they're traveling together. So basically dividing both sides by that combined mass, and now we have a velocity of 1.07 meters per second. Now, with that being said, we know that the kinetic energy is going to be converted to gravitational potential energy. So we know that the 1/2 mass times this velocity squared is going to equal our gravitational potential energy, which is mgh. And then for our h value, we're going to solve for the theoretical value that it's supposed to rise up to. So I left it as m because the m's are going to drop out anyways. So basically all we do is we divide both sides by 9.8. And then our height comes out to 0.06 meters. So it had a fairly small rise of 6 centimeters. Now, experimentally, what happened is we had it rise 5 centimeters from its original height. So let's go ahead and compare what happened with energy here. So theoretically, it was supposed to have an m, g, and h of 0.06, and then that would give it 0.0882 joules of gravitational potential energy. And then with that same combined mass of 0.15, the same constant of g, but the experimental height of 0.05, in reality, we actually got 0.0735 joules. If we subtract those, we would have a difference in energy of 0.0147 joules of energy. So that was some energy lost through heat and sound. So in that case, if we take the amount of energy lost divided by the total theoretical potential energy, and then that would give us 0.16 repeating, multiply that by 100, so that's about 16.67% decrease in its energy level. So that tells us a couple things. Number one, that tells us that it lost about 16.67% of its energy through sound and heat. And then secondly, it tells us that if we take 100 minus this, that would leave us with 83.33%. What that percentage would be describing would be the amount of kinetic energy that was converted to the gravitational potential energy at the end. So you can kind of look at it from two different perspectives. So as a quick recap, we had to apply a bunch of projectile motion ideas in order to define that initial velocity. That initial velocity helped us with our momentum approach over here to find the final velocity of the system once they combined. Now, once they combined with that final velocity of 1.07, that was the beginning of the energy calculations where it went from kinetic energy to gravitational potential energy. From there, we found the theoretical increase in height, compared it to the experimental, saw that it lost about 16.67% of its energy through sound and heat, and it was able to convert 83.33 of that kinetic energy initially into the gravitational potential energy. So I hope that was helpful to you. Thank you for watching and listening.